Imagine you're in a forest, camping. Suddenly, a tree falls and you hear this sound. Now, that's all good and all, but what if you weren't there to hear the sound? What if there was nobody in the forest? No human, ant, god, or creature of any sort? Then, if the tree were to fall, did it make any sound? This seemingly simple conundrum deals heavily with the nature of our senses. Your intuition might lead you to saying, yes, of course the tree makes a sound. But that answer is incorrect. The tree makes no sound. What the brain perceives as sound is vibrating air that hits our eardrum. The wave in itself is not sound, but it is perceived as a thing called sound when it hits an eardrum. But if nobody is around, there are no eardrums to be hit. So the falling motion of the tree will cause the surrounding air to jiggle, but that longitudinal wave of compressions and rarefactions will not bang into any eardrums, and so will never get to be perceived as sound by anybody. It will just exist for a moment. Now, say we did something similar with a light bulb. If we switched on a light bulb in an empty room with nobody and nothing, is the light bulb lit? Your intuition might lead you to saying, yes, of course the light bulb is lit. But that answer is incorrect. I'm just kidding. You're absolutely right. The bulb is luminous. Light does not work the same way as sound does. Sound is a wave, whereas light is, it's complicated. Remember ancient Greece, thousands of years ago, when everyone was thinking and this guy existed? Yeah, we're back here again, baby. Here, at around 300 to 400 BC, mathematicians thought that vision was caused due to rays extruding from our eyes and coming back. This idea, as was the case for many ideas in ancient Greece, was wrong. By this logic, the light bulb in the room isn't lit when nobody's looking at it. Despite this, the theory was adequate for a guy named Euclid to realize that light travels mostly in straight lines, and to work out the geometry of how light reflects and bends. Unlike the theory itself, Euclid's work was actually quite accurate and is still used eons later today. Light can bounce off of objects. This is called reflection, and it was Euclid who derived the law of reflection, which states that light reflects off of a surface at the same angle with which it is hit. Mathematically, angle of incidence, theta I, equals angle of reflection, theta R. This, though, only holds true for smooth surfaces, when we see regular reflection and not irregular reflection. The theory that light emerges out of our eyes was disproved by a damn influential Muslim Arab named Al-Hasan ibn al-Haytham, born in 10th century Iraq. This was the apparatus for one of Al-Haytham's experiments, a dark room with a hole in the wall through which two beams of light passed, each seen as individual spots on the inside. If you cover one of the sources, its spot disappears. This proves that light isn't about us and our little eyes, unlike how sound is about us and our ears. Light is not an extension of our bodies. Our eyes are just receivers of it. Al-Haytham conducted a bunch more experiments, writing nearly 100 books, including the Book of Optics. He is often regarded as the first true scientist. Yeah, I told you his work was damn influential. He even inspired Leonardo da Vinci. We see things because light bounces off of them and then goes into our eyes, where our brain creates an image. Light can travel through stuff like air, water, glass, diamonds, etc. Any transparent material is just a thing that lets light pass through it. When you switch on the light bulb, it really seems like light travels instantaneously to your eyes. And for a long time, that's what everyone believed. Light was thought to be instantaneous, but that is indeed wrong. Light has an exact finite speed. The speed of light is equal to 299,792,458 meters per second, denoted c. That is inconceivably fast. You cannot appreciate how ridiculous that is. In its lifetime, the average car today will drive about 284,000 kilometers. You know how long it takes light to cover that? Yeah, under a second. The furthest humans have ever traveled from the Earth is the moon. It's about 384,000 kilometers away. And it takes light just over 1 second to travel that far. Yes, the furthest we humans have ever traveled from Earth is just 1 light second away. The moon takes a month to orbit around the Earth. You know how long light will take? 1 second. Just kidding. It'll take 0.13 seconds. Light is fast, but this number, 299,792,458 meters per second, is how fast light travels in a vacuum. In the void of outer space, where there is no medium, the speed of light is c. But here on Earth, there is no void. We've got an atmosphere of air particles. And in this medium, light slows down a bit. Not much, just a little bit. You see, here it will travel at 299,702,520 meters per second. In water now, light slows down considerably, traveling at only 224,844,344 meters per second. Light is hella fast, but it's also hella lazy. When traveling between any 2 points in space, light will always take the path of least time. Light wants to minimize the time taken in traveling between any 2 points. This principle is called Fermat's Principle, named after the guy who discovered it, Pierre de Fermat. This principle gives rise to some very weird phenomena. Look at this glass of water. The pen in it looks bent and disjointed. Why is that? Well, when light rays bounce off this pen and go into our eyes, they will not take this path. Remember, Fermat told us that light takes the path of least time. And as we remarked earlier, light is slower in water than in air. It won't take this path either, because although it spends the least time in water, it spends a long time in the air. Instead, it'll take this path. Here, the combined times spent in water and air will be lesser than any other path. And as light takes this path, it bends noticeably. As a result, our brains are quite confused about the positions of the portion of the pen immersed in water. Because light obeys Fermat's principle, it bends when entering different media. This phenomenon is called refraction. Mathematically, we can study refraction using Snell's law, named after the 17th century Dutch astronomer Wilbrord Snellius. Man, what a name that is. So you have a glass of water and shine a beam at it. The light bends as it passes through air into water. Then we can draw an imaginary line called the normal that's perpendicular to the surface of the water. Now we can measure the angle of incidence, theta air, and what we call the angle of refraction, theta water, in relation to this normal. Claudius Ptolemy, thousands of years ago, does this for a wide range of angles, and he then tries to find a relationship between theta air and theta water, to no avail. Many centuries later, Snellius comes along and says that there is a relationship between the sine of theta air and the sine of theta water, and it's this: n air times sine of theta air equals n water times the sine of theta water. What's n? N stands for the index of refraction, which is the speed of light in a vacuum divided by the speed of light in any specific medium. The index of refraction of a vacuum is obviously 1, because it's the speed of light in a vacuum divided by the speed of light in a vacuum. For air, it's 1.00029, and for water, it's 1.33. Let's play around with this formula. You've lost your shoe in a pond and you want to fetch it out. You've located exactly where it is using your flashlight, but you want to know how deep the pond is before you jump in and get it, because that way you'll know whether your magnificent hair will get wet. Here is all the information we have about the system. You are holding the flashlight 1 meter above the pond. The shoe is located 10 meters from where you're standing, and the distance that the light beam is traveling from the flashlight to the surface of the pond, known as the incident point, is 8.1 meters. The shoe is right at the floor of the pond. So we have to calculate the depth of the pond using these 3 pieces of information. I recommend that you pause this video and attempt to solve this question. The first thing we can do is indirectly calculate the angle of incidence of this light beam. We know that theta r plus phi will equal 90 degrees. Using the trigonometric function of sine, we can see that phi is equal to 7.1 degrees. Subtracting that from 90, we get that the angle of incidence is 82.9 degrees. Now we can calculate the angle of refraction using Snell's law. We know that the index of refraction of the two media here, air and water, to be 1.00029 and 1.33 respectively. Plugging that in alongside the sine of the incident angle into Snell's law, we see that the angle of refraction is 48 degrees. We have arrived at the home stretch of this problem. We can now calculate the distance between you and the incident point of the light beam, x, using Pythagoras' theorem. We get that it is 8.04 meters. We can subtract x from 10 meters to get y, the distance from the incident point to the shoe. Y is 1.96 meters. Lastly, we can plug in y and the angle of refraction into the trig function tangent to get the height of this right angular triangle, the height of the pond. The height of the pond, h, now is 1.765 meters. Your height is only 1.5 meters and you cannot swim, so you'll basically have to walk in the water to get the shoe. You and your magnificent hair are sadly going to get wet. Alright, we've assumed all throughout that light just slows down upon entering different media. I mean, it is still ridiculously fast everywhere, but that's besides the point. Why does light slow down in different media in the first place? Why does it have to give rise to Snell's law and refraction? To answer this question, we need to first realize that beams of light are not really rays like how we've been modeling them so far. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I have also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.